Hello and welcome to lecture 6 of the course on quantum entanglement and non-local games. Here we will continue the proof for the rigidity of CHSH game, which we started with in the last lecture. So if you recall, we divided the proof into 4 parts. So if you look back, so first we plan to show that it suffices to assume that there is an ensemble of projected measurements on states with full Schmidt rank. So this is something which we have already proven. Next, we are going to show that assuming step 1, that is assuming that we can deal with binary observables, right? Because projective measurements can always be expressed as binary observables. We can show that the binary observables corresponding to 0 input or 1 input. For Alice, they are going to anti-commute. So this is something we are going to do now. And once they are anti-commuting, then we can show that they are of the form X and C. And in this case, the operators for B0 and B1 will also have the required form, and the entangled state is going to be EPR pair. So we'll go through the rest of the steps now. In the end, we'll need to prove a couple of lemmas also, so that probably I'll leave for the next lecture. But yeah, so I'll mostly be done with the main part of the proof today. Okay, so let's continue this. So here, so we assume that Alice and Bob share an entangled state psi sub AB, and Alice and Bob have their binary observables so actually an ensemble of binary observables, right? Because we can show that any POVM can be expressed as an ensemble of projective measurements. So here, in fact, this entangled state is also has full Schmidt rank. So A and B have an ensemble of binary observables, okay, and they have an ensemble for each of the inputs. So Alice has, depending on the input S, so S can lie in either 0 or 1. So for whether S is 0 or 1, Alice has a different ensemble of observables, and Bob has an ensemble of variables P sub R subscripted by T. So T is 10, 0, 1. So R is a shared random string which they are using to decide which observable amongst their set of ensembles they need to take. And now, if they actually achieve optimal bias, that means that average over all these random variables R, the bias is going to be 1 over root 2. So basically, what we have is that sum over R, there is a probability distribution which I can associate with R. So this probability distribution is coming from the conversion of our POVM to ensemble of projective measurements, right? So we saw that we have to diagonalize the POV as mu1 up to mu d, and those mu i's, they actually help us defining a distribution over the random variable R. So average over R, the bias corresponds to now psi AR0 tensor BR0 plus AR0 tensor BR1 plus AR1 tensored BR0 minus AR1 tensored BR1. So this is going to be our overall, this is going to be the bias, and this bias we know is 1 over root 2, right? But now we know that each of these quantities is less than equal to 1 over root 2. but their average is exactly 1 over root 2, right? So each of these has to be exactly 1 over root 2, right? For all r, we have that psi AR0 tensor BR0 plus AR0 tensor BR1 plus AR1 tensor BR0 minus AR1 tensor BR1 psi equals to 1 over root 2, right? So this is happening for each of r, for all r. And why is it so? Because if any of them is strictly less than 1 over root 2, then average is going to be strictly less than 1 over root 2, right? And none of these can be greater than 1 over root 2. So they have to be exactly equal to 1 over root 2, right? And this allows us to assume that there is actually a so without loss of generality, I can just pick one of these set of binary observables, and then this will give me the optimal outcome anyways. So we can actually, for now, we drop superscript r. So this is already implicit. Okay, so let's just work with an ensemble which consists of a single binary observable, because anyways whatever we can do with single, we can also do whatever we can do with ensemble, we can also do with a single observable per input. So now we saw this big question. So actually what I'll try to do is that I'll try to express this in a more simple form. So in the inner part, if you recall, we had A0 tensored B0 plus A0 tensored B1 plus A1 tensored B0 minus A1 tensored B1. And I can actually write this as A0 tensor B0 plus B1 plus A1 tensor B0 minus B1, and there is a 1 over 4 overall. Okay. So what I can do is that I can actually break it down as follows. So I can write it in a block form. So I can write it as A0 tensor I, A1 tensor I times so here I have I tensored B0 plus B1 and I tensored B0 minus B1, and there is a factor of 1 over 4. So what I'll do is that I'll take a 2 with the first matrix and 2 with the second matrix. So half and half, I'll just take it, right? And I know that if I sandwich psi between this thing, psi inside and outside this, what I actually get is that psi with the above block matrix multiplication, psi this equals 1 over root 2. So what I can do is that I can just take 1 over root 2 here. Okay, I multiply both sides by 1 over root by root 2, and this gives me 1. So overall what I am getting is that psi, and then there is a block thing, A0 tensored I by root 2, A1 tensored I by root 2, and I tensored B0 plus B1 by 2, and I tensored B0 minus B1 by 2. This thing with psi is going to be 1. Okay. And now what I do is that I define this quantity, this matrix term, as MB, and the column part of this is something which I define as MA. So what I do is that I define MA as I take the transpose of this somehow. So what I'm going to get, A0 tensor I by root 2, A1 tensor I by root 2. So this is what is my definition of M sub A, and M sub B is defined as I tensor B0 plus B1 by 2 and I tensor B0 minus B1 by 2. Okay, so we are just defining two matrices, and notice what's the size of each of these. So we know that A naught is essentially, say, a d-dimensional observable, so CD cross CD, and so this is in Bob Hilbert space now, this is also d CD cross CD, and so for A1 as well. So overall, if you see the size of this thing, so this is going to be now overall this is also in CD cross CD, tensored CD cross CD. So overall this will be C2D cross CD tensored with CD cross CD. MB will also have the same size, right? C2D cross CD tensored CD cross CD. Now you can verify for the MA and MB which have been so defined, we can check that MA, dagger MA is identity and MB, dagger MB is also identity. So here you will have to use the fact that AIs and BIs are binary observable. So use that A0 square is I and A, or let me write AI square is I and AI dagger equals to AI for I in 0 and 1, and similarly for BI also. Okay, same for B also. So once you use these conditions, it's very easy to verify that MA dagger MA is identity and MB dagger MB is also going to be identity. Now with MA and MB which have been so defined, I can actually define my ket V and ket W. So ket V is defined as MA acting on psi and ket W is defined as MB acting on psi. Okay. Now the why have I defined these things? Because now you can check that this right part will correspond to ket W. So this is MB acting on psi, and this is the dagger of MA acting on psi on brass psi. So overall this will be ket V. So here just by the definition and the result which we have just expressed over here, we can actually observe that V dot W equals to 1. Okay, and from these two you can actually check that V dot V is going to be 1, right, because psi, so V dot V is going to be psi MA dagger MA psi, right, and MA dagger MA is identity, and so this is just psi dot psi which is 1, and similarly W dot W is also 1. So both V and W are now unit vectors and V dot W is going to be 1. Okay, so these two relations I have already left as homework, And one more thing is that once you have these two relations, you can check that these are essentially isometries. So MA and MB are both isometries from D tensor D space to 2D tensor D space. And when you have an isometry, what it means is that it actually preserves all the distances and angles. It need not be a vector space isomorphism because it need not be onto, right? But it is actually 1, 1. Okay. So here what we now have overall now in the way we have defined V and W, we have seen that V dot W is 1, norm V is 1, and norm W is also 1. Now by Cauchy-Schwarz inequality, what we have is that V dot W mod is less than equal to norm V times norm W, right? But here the Cauchy-Schwarz, this instead of an inequality, this relation holds as an equality because left hand side is also 1 and right hand side is also 1. And we know that Cauchy-Schwarz can hold as an equality only when V is proportional to W. Okay, so what we have is that V is some alpha times W, right? But since now V dot W, that is going to be alpha, and alpha is now 1 because V dot W is 1. So therefore we have that V and W, they must be equal, right? So until this point I think it should be clear. If not, do pause the video and try to understand here what we have done so far. So overall what that is going to mean is that, so by definition this V was, so this ket V was essentially MA times psi, and this equals MB times psi. Okay, and what is MA again? This is A0 tensor I by root 2, A1 tensor I by root 2. This thing acting on ket psi equals I tensor B0 plus B1 by 2, I tensor B0 minus B1 by 2. This thing acting on ket psi. So this gives us actually two equations. First is that A0 tensor I by root 2 acting on ket psi equals I tensor B0 plus B1 by 2 acting on ket psi. And A1 tensor I by root 2 acting on ket psi equals I tensor B0 minus B1 by 2 acting on ket psi. So from these two equations, can we deduce something? So for this we are actually going to need a lemma. So this lemma says that for ket psi, with full Schmidt rank, and unitaries A and B, we have that if A tensor I psi equals I tensor B psi, then A equals B transpose. So from this result, what we have is that A0 by root 2 equals B1 plus B2 by 2 transpose, and A1 by root 2 equals B0 minus B1 by 2 transpose. Okay. So B0 plus B1. So actually we haven't yet proved this lemma, so this will be proven in next lecture. Will be proven in next lecture. So B0 plus B1 by 2 should equal to A0 by root 2 transpose, which means that B0 plus B1 by root 2 equals to A0 transpose. And the second equation is going to give us that B0 minus B1 by 2 equals A1 by root 2 transpose, which means that A1 transpose is B0 minus B1 by root 2. Okay, so note that this lemma holds because psi is a full Schmidt rank vector, and that is why we needed that assumption. Okay. Okay, so these two equations now hold, and now if you multiply these equations, what you are going to get is that A0 transpose times B0 transpose. So A0 transpose times A1 transpose is going to be B0 plus B1 by root 2 times B0 minus B1 by root 2. So we are going to get B0 square, which is identity, minus B1 square, which is also identity. So overall this will be B1 B0 minus B0 B1 by 2. And A1 transpose A0 transpose, if I do, then this is going to reverse the order. So again B0 square and B1 square, they are going to cancel, and now what I have is B0 B1 minus B1 B0 by 2. Okay, so what we have then is that A0 transpose A1 transpose equals to minus of A1 transpose A0 transpose, right? So this is the negative. These two equations are negative of each other. So what I have is that A0 A1 whole transpose is minus of A1 A0 whole transpose, and so A0 A1 equals to minus of A1 A0. Okay, so A0 and A1 here, they anti-commute, right? In fact, this was what we called as the step 2 of our proof. Okay, now step 3 of the proof is actually, I'll just state it in a lemma and I'll complete that in the next lecture again. For two binary observables, A and B, if AB equals to minus of BA, then there exists a unitary U such that U dagger AU equals to X tensor IM and U dagger BU equals to Z tensor IM. Right, so this lemma is actually applicable, right, because A0 and A1 are binary observables and they anti-commute, and so these two conditions are met. So therefore, with respect to some unitary, we have that they are essentially X tensor IM and Z tensor IM for some M. Okay, so in some basis they are like just applying Pauli operators on the first qubit and then just ignoring the rest of the qubits. So then what happens? We have that so A0, so U dagger A0 U equals to Z tensor IM from the above lemma. So then there exists a U such that U dagger AU is Z tensor IM, U dagger A1U is X tensor IM. So now so from here I can write A0 as U Z tensor IM U dagger. A1 I can express as U X tensor IM U dagger. Okay, and then what we have is that B0 plus B1 by root 2, which was A0 transpose, would be equal to U times Z tensor IM U dagger whole thing transposed. Okay, so this is nothing but U transpose, and Z transpose is just Z, right? So U transpose Z tensor IM and U transpose dagger. So U transpose dagger is same as U dagger transpose. And similarly, from the other equation, we are going to get B0 minus B1 by root 2 equals to U transpose X tensor IM U transpose dagger. Okay, and now I can actually add and subtract to solve for B0 and B1. So please verify this, that this is indeed true. So when you will add and subtract, you can actually get that B0 equals U transpose dagger X plus Z by root 2 tensor IM U transpose, and B1 equals to U transpose dagger X minus Z by root 2 tensor IM U transpose. And this X plus Z by root 2 is nothing but H. So verify that this is indeed true, and this is nothing but ZHZ. So now in the U transpose basis, they are looking like Zn ZHZ, whereas in the U basis, our Alice's operators look like X and H. But these are essentially local on their own Hilbert spaces. Okay, so we have found out these U and V under which they behave like X, Z, H and ZHZ. So that is done. And now we just have to show that the vector ket psi must correspond to an EPR pair. Okay. So now ket psi must satisfy that psi A0 tensor B0 plus A0 tensor P1 plus A1 tensor P0 minus A1 tensor B1. Okay, this thing over 4 psi. This must be 1 over root 2. So we have already found out AIs and BIs in a given basis. Okay, so substitute A0 as Z, A1 as X, B0 as H, B1 as ZHZ. Okay, and now we can compute this big expression A0 tensor B0 plus A0 tensor B1 plus A1 tensor B0 minus A1 tensor B1, this whole thing upon 4. Okay, so if you compute this thing, what you are going to get is that you are going to get 1 over root 2, and you have this big 4 cross 4 matrix now, and you will have it of the form half 0 0 half, and 0 minus half plus half 0 0 plus half minus half 0, and half, this is plus half 0 0 half. Okay, so now you can compute the eigenvalues of this matrix. So you can just use some NumPy or maybe any Wolfram Alpha or any like some kind of like linear algebra sort of software, and you can compute the eigenvalues as plus minus 1 by root 2 zeros. So it has 4 distinct eigenvalues, plus by root 2, minus 1 by root 2, 0 and 0. And here essentially psi times this matrix times psi is going to be so the largest value which we can get will correspond to its the largest eigenvalue, which is 1 over root 2, and here this is what we want, right? So the value of ket psi which can achieve this is the eigenvector corresponding to 1 over root 2. So if we look at the eigenvector for 1 over root 2, and that we will get to be 1 over root 2, 1 0 0 1. So this is a normalized eigenvector, a unit eigenvector which I am taking, and this corresponds to psi equals to 1 by root 2 0 0 plus 1 by root 2 1. And of course there is a, it can be tensored with a phi chunk. So here we can actually tensor with a phi chunk. So the reason being that because there is a tensor Im which is always associated here. So if I keep that till the end, so there has to be a tensored Im here also, right? And overall I'm looking for the eigenvectors of this thing tensored with Im. So this tensored Im is already there, so I can actually have a vector in CM tensor CM space. So this phi vector, phi junk vector can always be there, so that's not an issue. But overall, if you see for the first qubit, it just corresponds to having an EPR pair and Alice and Bob measuring in the corresponding operators which we have seen earlier, right? And we have seen that this is the only strategy up to a unitary transformation. So for now, in order to complete the proof, we need to now show a couple of lemmas. The first one being that if the operators anti-commute, then they are of the form x and z. So this is one thing which we need to show. And yeah, and also we need to show that if psi is a full Schmidt rank vector, then there are unitaries A and B. If they satisfy A tensor I psi equals I tensor B psi, then A must be B transpose. Okay. And here, in order to show this, if you recall from the very first lecture that we did 3 lemmas, right, when we defined the maximally entangled state, and those lemmas will be crucial again in order to prove this specific lemma. So we need to just prove these 2 lemmas which we have used today, and we'll have another lecture where I'll just prove the 2 lemmas, and that will finish the proof for rigidity of CHSH game. Okay, thank you.